Hello students, welcome to the course in System Identification and Optimal Estimation. All the course information will be given on the course homepage, located on home.hit.no. This one, HIT, is obsolete, but this course, this link is as usual. @ tilde David R, my name, and SCE 2206. Here the lecture plan and syllabus, links to lectures will be given. To be strict and also exercises will be taken from a sheet like this, with about 10 exercises in this one. There also will be given some exercises from notes like this. So, and today I will introduce this exercise 1, also with some solution proposals. And what is system identification? System identification is the theory to build dynamic models from observed data. And you know about simulation. You have a model and some inputs, and you can simulate and generate output data. But the system identification is sort of the inverse problem. From the data, can identify a model. So let us take a look at the system. Very often I think about the system as a black box like this, with some variables we can influence, input variables called U, and this U may be a vector. And in system identification, those inputs are usually in discrete time. We indicate the discrete time index lowercase k here, and from the inputs we may influence the system and generate output data in vector y at discrete time k. And we will assume that this system is dynamic, so there is internal states in order to treat the dynamic behavior from the inputs to the outputs. We have a state vector x, also at discrete time k. We may have noise influences or noise influencing the system. But for the first time, I will not treat inputs. But if we have inputs, we have some arrows up here. Okay, the inputs and outputs, U and Y, may be vectors. Very often I define a vector like this. U1 and U2 ... down to UR. This is a vector, it's a column. Also remember in the on the course homepage, there also is a link to some details about matrix definitions, about vectors and matrices and so on. And this one is formally defined as the element of real numbers of dimension m This is a formal way of defining a vector. So this is known input variables. At discrete time k. Similarly with the output vector y at time k. I should take an index k here to indicate discrete time. This is also a vector with y1, 2, and to ym. So here R is the number of input variables influencing the output variables, and M is the number of output variables. Formally, this one may be defined. Sorry, an error here. I should have R here and M here. This is known output in vector y. The problem in system identification. System identification is very often short as an S for system, an ID for identification. So let me write this seed problem. From known input and output variables uk and yk, but we need a number of observations. This sign, this is called for all discrete time instants from k equal to 0 and time 1, 2, ... And very often I assume a number, uppercase n, number of observations, so then n minus 1. This means that we have here n known input and output. So from this knowledge, identify a model of this system. And this system is, of course, is in general dynamic. So I could have written identify a dynamic model, but models is usually dynamic in nature. So identify a model from the known input and output data. Remark here. We could have defined the vector of states also in the same way. So the vector of states x is state 1, state 2, and possibly n states. xn, lowercase n, is the number of states. This may formally be written this vector as an array of real numbers. So this is the state vector. And n, this is important, is defined as the system order. And remember, this system order is unknown. Now, in my when I wrote this problem definition, this is a rather general and complicated problem. So we have to restrict or do some assumptions about this system. You see, you have simulated systems, you have non-linear models, and there may be an infinite number of non-linearities. An infinite number of structures. So we have, in order to solve the system identification problem, we have to restrict ourselves. And you know that non-linear models may be linearized. There exist linear approximations of non-linear systems. So let us restrict ourselves to linear systems. So we assume this system may be approximated by a linear and discrete time. Linear, discrete time. And probably, or I know, in my opinion, the best way of describing linear systems, it is in state space. So I will restrict the problem to linear discrete time state space models. And in linear state space discrete time models, this system may be approximated with a state equation x at time k plus 1 equal to a xk plus b uk, like this. And there is an output equation where the output vector is dxk. Some textbooks are using C, or some teachers are using C. I'm using D as the symbol for the output matrix. And plus EUK. Sometimes there may be a direct influence from the input vector U to the output in this way. Not always. In order to generalize a little bit here, if I introduce noise influencing this system, we have two noise variables usually influencing a system. We have so-called process noise, which I aim as V at discrete time k, and measurements noise WK. So let me introduce those noise variables in this state space model. We can have plus CVK. And here you will also in a moment observe the reason for this ABDE notation. So ABC DE plus FWK then. could be like this. A, B, C, D, E, F. Yeah. Let me, now we can define our problem in more details. Now we have specified a structure for this system, a model structure. You see, those noise processes will be treated in more details later on. But I can maybe write here that Vk is process noise. And the noise variables are unknown. And Wq, measurements noise. Those noise processes are usually unknown. I simply write unknown. So in order to treat the noise influence, we also have to do some assumptions about the noise influencing the system. Very often we assume that the noise influencing is random. Yeah. So the SID problem. From known input-output data. UK, YK, and write it like this also for all observations. Very often I wrote from 0 to n-1. Sometimes I also start at the discrete time instant 1. It will be the same model. Identify, or I can take a parenthesis from k equal to 0 to n-1 is the same. Identify. First of all, we have to find some information about the number of states in the system. The system order n. Identify the system order and the model matrices. A, B, C. I usually order at very often the most important part of such a general discrete time model is A, B, D, E, which describes the behavior from the input to the output. So very often I write A, B, D, E like this, and also C and F. All those matrices should be identified from the input-output data. This is the most general problem, which we will treat during this course in the system identification part. Let us now skip the influence of noise, and I will look at what we call a deterministic system. A system without influencing of noise, and do some definitions. So if I go back to this model, And I will do some definitions necessarily for solving exercise 1. Yeah. And the keywords here is impulse response matrices. So let us define what we call the impulse response matrices of a system. Is in fact the product of dB and dAB, dA square B, and so on. And I use H as the symbol for impulse response matrix. Like this. This is an impulse response matrix. And the dimension of this impulse response matrix is a matrix with m rows and r columns, like this. A rule for finding dimensions, the dimension of the product of matrices, is very simply done as follows. Remark. When multiplying matrices, and dimensions, or in order to, you don't have to remember that this one is m by r. If you don't remember, you can take a dimension analysis. Do you see this matrix D? It is a matrix like this. Now I defined y as a vector with m rows. So this one, you will have m rows in D also. So if this is a vector with m rows, then this one will also be a vector with m rows. X is a vector with n elements. So then the number of columns in D would be n, like this. And this a in power k minus 1 is a square matrix because a is n by n. So xk plus 1 will be an n vector. An x n vector, then a is n by n. You can write up the dimension here and here. Similarly with B. And looking at B, you'd have n rows. You have a vector with r elements, so B should be n by r. Like this. And then you see, in order to multiply two matrices, the number of columns has to be equal to the number of rows. And it is. You can cancel this one. Also here. So the result is, which we have called H, okay, would be m by r. QED, or it's a nice rule. Why is those impulse response matrices important in a model like this? This model is called a deterministic model. You see, a model without the influence of noise can be defined as a deterministic model. Everything is known, all influencing and the odd. So this is defined as a deterministic model. Let us take a look at and show how the impulse response matrices arise from the model. You see, at time k equal to 0, we have, looking at the output equation, we have then at the output at time 0, d times x d at time 0 plus e u at time 0. Also, we have that the state at discrete time 1 then is a x 0 plus e u 0. Here, you see, in connection with models, remember back to the time when you simulated dynamic models, you had to specify the initial state vector. You see this x0. I have said that the u's from time 0 to n minus 1 is known. And then the outputs from 0 to n minus 1 would be generated only if this initial state is specified. So this x0, the initial state, and it is a vector. And this initial state is also unknown. So it is a part of the problem to identify this initial state. And now at time k equal to 1, then, we have that y1 is dx1 plus du1. I'm putting in x1 here. We obtain d a x0 plus d du0 plus u1. Let us take also at discrete time k equal to 2, then. And we obtain the output at discrete time 2 as dx2. And we need the state at discrete time 2. Can write it here. Or a line up here. This, and then we have dx1 plus dbu1 plus, I think I have forgotten e plus eu2. This. And we have dax1 plus du1 plus eu2 And we also can put in x1 here from this equation. And then we have that the output at discrete time 2 is dA square x0 plus dAb u0 and plus dB u1 plus E u2. And we can continue like this up to our last observation n, or n minus 1 then. But I define the impulse response matrices as the product of D and A in the power k minus 1 like this. So we see that dB, dAb, the same as this equation. So hence, this means that also E is in fact an impulse response matrix. So here E, product of dB, dAb, etc. are impulse response matrices. And we can continue, of course, and then we will find this one. And we can have here for all k's equal to, if I here, I could have used a different integer here. But anyway, from time 1 then to, we have impulse response matrices. So the impulse matrix with k equal to 1 is then D times B, because A in 0 is the identity matrix. Is 1. Is this one. And with k equal to 2 here, we obtain the dAb. And why is those matrices called impulse response matrices? That is a detail I will commenting open. The reason is that those matrices may simply be identified by feeding an impulse into the system. Why? Why the name impulse response matrices? The reason is that those impulse response matrices may simply be identified fed by feeding an impulse input to the system. At least in theory, as I will show you now. You see, an impulse, assume, as an example, or assume as follows. Very often not usually or always. We stack the inputs and outputs in data matrices. I could have, so let me speak a little bit about this. So suppose that we have stored the observations of the inputs in a vector like this. U at discrete time 0 and U at time 1 like this, and down to the last observation U at n minus 1 then. Sorry about this. Sorry students, I think I am logged out here also. I can record. Don't think.